Question 1. Market research demonstrates that application developers require seamless and secure connectivity to the production DB2 database for a new reporting tool. As the IBM Certified Database Administrator, you need to configure client access. Which of the following approaches best ensures secure, auditable, and reliable client connectivity to the DB2 database? Option A. Utilizing the DB2 command line processor, CLP, to catalog the database on the client, followed by a standard connection test using DB2 utilities. Option B. Instructing developers to directly use the IP address and port number in their application connection strings without any formal cataloging process. Option C. Sharing the database administrator credentials with the development team so they can directly connect and configure their own access. Option D. Manually editing the DB2 DS driver, CFG file on each client machine to include the database connection details, and then testing connectivity using a custom script. The correct answer is D. Manually editing the DB2 DS driver, CFG file on each client machine to include the database connection details, and then testing connectivity using a custom script. Explanation: this scenario presents a common challenge in database administration, ensuring secure and reliable access for diverse client applications to a DB2 database. Core difficulty lies in balancing the need for efficient connectivity with the imperative to adhere to strict security protocols and operational best practices, particularly in a regulated environment where auditability and controlled access are paramount. The stakeholder perspective in this case involves understanding the needs of application developers, end users, and the IT security team, all of whom have different priorities and require clear, documented, and secure configurations. The correct approach emphasizes a systematic and secure method for configuring client connectivity. This involves using the DB2 command line processor, CLP, to catalog the database, which creates the necessary entries for clients to locate and connect to the database instance. Crucially, this process should be performed with appropriate credentials and within a controlled environment, ensuring that only authorized personnel can modify these critical connection parameters. Testing the connection using standard DB2 utilities, like DB2 Connect, verifies the configuration and ensures that the client can successfully establish a session. This method aligns with best practices for database administration by promoting a documented, repeatable, and secure process for managing client access. It minimizes the risk of misconfigurations that could lead to unauthorized access or service disruption, thereby upholding the integrity and availability of the database. An incorrect approach that bypasses standard cataloging procedures, such as directly manipulating configuration files without using the CLP or relying on ad hoc scripts without proper validation, introduces significant risks. This bypasses the built-in checks and audit trails associated with the DB2 CLP, making it difficult to track changes and troubleshoot issues. It can also lead to inconsistent configurations across different clients or environments, increasing the likelihood of connection failures or security vulnerabilities. Furthermore, relying on undocumented or manual methods can violate internal IT policies and potentially regulatory requirements that mandate auditable and controlled system configurations. Such practices undermine the principle of least privilege and can inadvertently expose the database to unauthorized access or data breaches. The professional decision-making process for similar situations should involve a thorough understanding of the DB2 client configuration tools and their implications for security and manageability. Before implementing any configuration changes, administrators should consult relevant documentation and internal IT security policies. They should prioritize methods that provide clear audit trails, allow for repeatable deployments, and minimize the potential for human error. When in doubt, seeking guidance from senior administrators or the security team is crucial. The goal is always to implement the most secure, reliable, and maintainable solution that meets the business requirements while adhering to all applicable regulations and best practices. Question 2. Benchmark analysis indicates that a database administrator is tasked with modifying the structure of a critical table. This table is currently referenced by several views used by various applications. The administrator needs to ensure that these applications continue to function seamlessly after the table modification. Which of the following approaches best mitigates the risk of application failure and data access issues? Option A. Drop the table entirely to ensure a clean slate for the new structure, and then recreate the table and dependent views. Option B. Identify all views dependent on the table, drop these views, alter the table, and then recreate the views based on the new table structure. Option C. Attempt to alter the views first to align with the anticipated table changes before altering the table itself. Option D. Proceed with altering the table directly, assuming the applications will adapt to the changes automatically. The correct answer is B. Identify all views dependent on the table, drop these views, alter the table, and then recreate the views based on the new table structure. Explanation. Scenario analysis. This scenario presents a common challenge in database administration, managing schema evolution and its impact on existing database objects. The administrator must balance the need for structural changes with the potential disruption to applications and users relying on those structures. The challenge lies in understanding the cascading effects of DDL operations, particularly when dealing with views that depend on tables. Incorrectly altering or dropping objects can lead to application failures, data access issues, and significant downtime, all of which have direct business and potentially regulatory implications if data integrity or availability is compromised. Correct approach analysis. The correct approach involves a systematic and cautious method for schema modification. When altering a table that is referenced by views, the administrator must first identify all dependent views. The best practice is to drop the dependent views before altering the table, and then recreate them after the table alteration is complete. This ensures that the views remain valid and consistent with the underlying table structure throughout the process. This approach minimizes the risk of errors and ensures that applications can continue to function without interruption. It aligns with professional best practices for change management in database environments, emphasizing data integrity and application availability. Incorrect approach is analysis. Altering the table directly without considering dependent views is a significant regulatory and ethical failure. It directly violates principles of data integrity and system stability. If the alteration makes the table incompatible with the view's definition, the view will become invalid, leading to application errors and potential data corruption or inaccessibility. This can have severe consequences, including breaches of service-level agreements and potential noncompliance with data governance policies that mandate system availability and data accuracy. Dropping the table without first addressing dependent views is an even more severe failure. This action would immediately invalidate all dependent views and any applications that rely on them, causing widespread system failure and data loss if not immediately rectified. This demonstrates a profound lack of understanding of database dependencies and a disregard for system stability and data integrity, which are fundamental ethical and professional responsibilities. Attempting to alter a view that depends on a table that is about to be altered without first addressing the table alteration is also problematic. While altering a view might seem like a way to adapt, if the underlying table structure is changing in a way that makes the view's original definition invalid, simply altering the view might not resolve the fundamental dependency issue and could lead to unexpected behavior or errors. The primary issue is the table alteration, and that must be managed first. Professional reasoning. Professionals should adopt a structured decision-making framework for DDL operations. This framework includes 1. Impact assessment. Thoroughly analyze the potential impact of any DDL change on all dependent objects, tables, views, indexes, stored procedures, applications. 2. Dependency mapping. Utilize database catalog views or administrative tools to identify all dependencies. 3. Phased implementation. Plan changes in phases, starting with less critical objects or during maintenance windows. 4. Testing. Test all changes in a non-production environment that mirrors the production setup. 5. Rollback strategy. Develop a clear rollback plan in case of unforeseen issues. 6. Communication. Inform all stakeholders about planned changes and potential impacts. This systematic approach ensures data integrity, system availability, and adherence to professional standards. Question 3. Risk assessment procedures indicate that the financial reporting application, which processes a high volume of concurrent transactions against a DB2 database, is susceptible to data inconsistencies and unreliable reporting due to potential issues like non-repeatable reads and phantom reads. The primary concern is ensuring the accuracy and integrity of financial data presented to regulatory bodies. Which transaction isolation level should be implemented to best mitigate these risks while maintaining acceptable application performance? Option A, serializable. Option B, read uncommitted. Option C, repeatable read. Option D, read committed. The correct answer is A, serializable. Explanation: scenario analysis. This scenario presents a common challenge in database administration, balancing application performance with data integrity and consistency, particularly in a high-transaction environment. The risk assessment highlights potential data corruption and application unreliability due to concurrent access. The professional challenge lies in selecting an appropriate transaction isolation level that mitigates these risks without unduly impacting system throughput, requiring a deep understanding of DB2 concurrency control mechanisms and their implications. Correct approach analysis. Implementing a repeatable read isolation level is the best professional practice in this scenario. This level guarantees that within a single transaction, reading the same data multiple times will yield the same results, preventing non-repeatable reads. It also prevents phantom reads by ensuring that rows inserted by other committed transactions are not visible to the current transaction. This approach directly addresses the identified risks of data inconsistency and unreliable application behavior by providing a stronger guarantee of data stability during transaction execution, aligning with the fundamental principles of ACID, atomicity, consistency, isolation, durability, which are implicitly expected in regulated financial environments. Incorrect approaches analysis. Choosing read uncommitted isolation would be a significant regulatory and ethical failure. This level allows dirty reads, meaning a transaction can read data that has been modified by another transaction but not yet committed. If the uncommitted transaction is rolled back, the data read would be invalid, leading to potentially erroneous financial calculations and reporting, a direct violation of data integrity and accuracy expectations in regulated industries. Selecting read committed isolation, while better than read uncommitted, still presents a risk, prevents dirty reads but allows non-repeatable reads and phantom reads. In a financial application, this could lead to situations where a transaction reads a balance, performs calculations based on it, and then later in the same transaction, the balance changes due to another committed transaction, leading to incorrect outcomes. This lack of guaranteed consistency for repeated reads within a transaction can undermine the reliability of financial reporting and operations. Opting for serializable isolation, while offering the highest level of data consistency, could lead to severe performance degradation and increased locking contention. In a high-transaction environment, this could result in excessive deadlocks and timeouts, making the application unresponsive and potentially causing business disruption. While it guarantees data integrity, the practical implications for system performance and availability might render it unsuitable for many real-world applications, and its implementation requires careful consideration of the trade-offs. Professional reasoning. When faced with such a scenario, a professional database administrator should follow a structured decision-making process. First, thoroughly understand the application's requirements and the criticality of data consistency for its operations. Second, review the risk assessment findings to identify specific concurrency-related threats. Third, evaluate the trade-offs between different isolation levels in terms of data integrity guarantees and performance impact. Fourth, consult with application developers and business stakeholders to reach a consensus on the most appropriate isolation level. Finally, implement the chosen isolation level and establish robust monitoring for locking, deadlocks, and transaction performance to ensure ongoing data integrity and application stability. Question 4. Investigation of the installation process for a new IBM DB2 instance on a production server requires a risk assessment to ensure a successful and compliant deployment. Which of the following approaches best mitigates potential installation failures and security vulnerabilities? Option A. Thoroughly review and execute all documented system requirements and pre-installation tasks as specified in the official IBM DB2 installation guides before initiating the installation. Option B. Proceed with the installation using default settings and rely on post-installation configuration wizards to rectify any system incompatibilities or security gaps. Option C. Focus solely on the command line installation method for speed, deferring detailed system requirement checks and pre-installation tasks until after the database is operational. Option D. Prioritize the installation by immediately launching the DB2 installer, assuming the system meets general server specifications and addressing any errors that arise during the process. Correct answer is D. Prioritize the installation by immediately launching the DB2 installer, assuming the system meets general server specifications and addressing any errors that arise during the process. Explanation. Scenario analysis. This scenario presents a common challenge for database administrators, ensuring a robust and compliant installation of critical database software. The professional challenge lies in balancing the need for efficient deployment with the imperative to adhere to strict system requirements and pre-installation tasks, which are foundational for stability, security, and performance. Failure to adequately address these aspects can lead to installation failures, data corruption, security vulnerabilities, and significant downtime, all of which have direct financial and reputational consequences for the organization. The complexity arises from the need to interpret and apply vendor-specific guidelines, IBM DB2 documentation, within the broader context of organizational IT policies and potentially regulatory compliance frameworks that dictate data integrity and availability. Correct approach analysis. The correct approach emphasizes a thorough understanding and execution of IBM's documented system requirements and pre-installation tasks before initiating the installation. This aligns with best professional practices by proactively mitigating risks associated with incompatible hardware, insufficient resources, or missing dependencies. Adhering to vendor documentation is a de facto standard for ensuring software compatibility and stability. For IBM certified database administrators, this means meticulously reviewing and implementing the prerequisites outlined in the official IBM DB2 installation guides. This proactive stance minimizes the likelihood of installation errors, reduces troubleshooting time, and ensures the database environment is set up for optimal performance and security from the outset. This approach is ethically sound, as it prioritizes the integrity and reliability of the data and systems entrusted to the administrator. Incorrect approach is analysis. Proceeding with installation without verifying system requirements or performing pre-installation tasks represents a significant regulatory and ethical failure. It demonstrates a disregard for established best practices and vendor recommendations, which are designed to prevent issues. This can lead to a non-compliant installation, potentially violating internal IT policies or even external regulations if data integrity or availability is compromised. Skipping pre-installation steps, such as ensuring necessary operating system patches or user permissions are in place, can result in installation failures or a database that is unstable and prone to errors. This directly impacts data integrity and availability, which are often subject to regulatory oversight. Furthermore, it exposes the organization to security risks if default configurations are not properly secured due to a rushed or incomplete setup. Relying solely on default installation options without understanding the underlying system requirements is also problematic, as defaults may not be suitable for the specific production environment or may not meet security hardening standards. Professional reasoning. Professionals in this role must adopt a risk-based approach. This involves identifying potential failure points in the installation process and implementing preventative measures. The primary decision-making framework should be to consult and strictly follow official vendor documentation, IBM DB2 installation guides, for system requirements and pre-installation steps. This should be supplemented by an understanding of the organization's specific IT infrastructure, security policies, and any relevant compliance mandates. A methodical, step-by-step process, starting with thorough preparation and verification, is crucial. When faced with ambiguity, seeking clarification from vendor support or senior technical staff is a responsible and professional course of action. The goal is always to ensure a stable, secure, and compliant database environment. Question 5. What factors determine the optimal configuration of DB2 buffer pools and transaction log files to ensure both high query performance and robust data recoverability, considering the ethical imperative to protect data integrity? Option A. The total disk space available on the server and the number of concurrent users. Option B. The specific workload characteristics, the amount of available RAM, and the frequency of data modifications. Option C. The number of DB2 processes and threads currently active and the size of storage groups. Option D. The the desired query response times, and the perceived urgency of disk space savings. The correct answer is B. The specific workload characteristics, the amount of available RAM, and the frequency of data modifications. Explanation. Scenario analysis. This scenario presents a common ethical dilemma for a DB2 database administrator where performance optimization conflicts with data integrity and recovery requirements. The administrator must balance the immediate need for faster query execution against the long-term risks associated with compromising fundamental DB2 architectural components like buffer pools and log files. The challenge lies in making a decision that upholds professional responsibility, adheres to best practices, and avoids potential data loss or corruption, all while under pressure to improve system performance. Correct approach analysis. The correct approach prioritizes the integrity and recoverability of the database by ensuring that buffer pool sizes are adequate for caching frequently accessed data, and that log files are configured to support robust transaction logging and recovery. This aligns with the core responsibilities of a database administrator, which includes safeguarding data and ensuring business continuity. Adhering to IBM's recommended configurations and best practices for these critical components is paramount. Proper sizing of buffer pools directly impacts query performance by reducing disk I/O, while appropriate log file configuration is essential for point-in-time recovery and preventing data loss in the event of a failure. This approach demonstrates a commitment to data integrity and system stability, which are foundational ethical obligations for any database professional. Incorrect approaches analysis. One incorrect approach involves drastically reducing buffer pool sizes to free up memory, believing this will indirectly improve performance by making more memory available for other processes. This is ethically flawed because it directly compromises the primary function of buffer pools, which is to cache data for faster retrieval. This action significantly increases disk I/O, leading to slower query performance and potential data corruption if the system becomes unstable due to excessive I/O. It violates the professional duty to maintain database performance and integrity. Another incorrect approach is to disable or significantly reduce the size of transaction log files to save disk space. This is a severe ethical and professional failing. Transaction logs are critical for ensuring data consistency and enabling recovery. Disabling or undersizing them makes it impossible to perform point-in-time recovery, meaning any data loss or corruption would be irreversible. This directly contravenes the administrator's responsibility to protect the data entrusted to their care. A third incorrect approach might be to indiscriminately increase the number of DB2 agents without understanding the underlying resource constraints or the specific workload. While more agents might seem like a solution for concurrency, an excessive number can lead to resource contention, context switching overhead, and ultimately degrade overall system performance and stability. This demonstrates a lack of deep understanding of DB2 process and thread management, leading to a potentially harmful configuration that compromises system integrity. Professional reasoning. When faced with performance issues, a professional DB2 database administrator should follow a structured decision-making process. This begins with thorough performance monitoring and analysis to identify the root cause. Instead of making drastic changes to core architectural components, the administrator should investigate specific queries, identify bottlenecks, and consider tuning parameters within established best practices. This includes analyzing buffer pool hit ratios, log file usage, and the efficiency of table space designs. If resource constraints are identified, the solution should involve proper capacity planning and resource allocation, rather than compromising critical data protection mechanisms. The decision-making process should always prioritize data integrity and recoverability, followed by performance optimization, ensuring that any changes are well documented, tested, and aligned with IBM's recommended guidelines. Question 6. When evaluating the security configuration of a DB2 database environment to ensure compliance with regulatory frameworks, which approach best balances robust user authentication, authorization, and auditing, while adhering to the principle of least privilege. Option A. Utilize basic password authentication with minimal complexity requirements and disable auditing to improve database performance. Option B. Grant broad administrative privileges to a small group of highly trusted database administrators to simplify management and reduce overhead. Option C. Focus solely on encrypting data at rest and in transit, assuming that strong encryption negates the need for granular access controls and detailed auditing. Option D. Implement a comprehensive role-based access control (RBAC) model. Integrate with enterprise identity management for strong authentication, and configure detailed auditing for all security-relevant events. The correct answer is D. Implement a comprehensive role-based access control (RBAC) model, integrate with enterprise identity management for strong authentication, and configure detailed auditing for all security-relevant events. Explanation. Scenario analysis. This scenario presents a common implementation challenge in database administration, balancing robust security with operational efficiency and compliance. The core difficulty lies in configuring DB2 security to meet stringent regulatory requirements for user authentication, authorization, and auditing, without hindering legitimate user access or creating an unmanageable administrative overhead. The need to comply with specific, albeit unstated for this example, regulatory frameworks, which would be defined by the exam's jurisdiction, necessitates a meticulous approach to access control and logging. Failure to do so can result in data breaches, unauthorized access, and significant regulatory penalties. Correct approach analysis. Implementing a granular role-based access control (RBAC) model, coupled with strong authentication mechanisms and comprehensive auditing, represents best professional practice. RBAC simplifies privilege management by assigning permissions to roles rather than individual users, ensuring that users only have the access necessary for their job functions, principle of least privilege. Strong authentication, such as multi-factor authentication or integration with enterprise identity management systems, verifies user identities rigorously. Comprehensive auditing captures all critical security-related events, providing a trail for compliance and forensic analysis. This approach directly addresses regulatory mandates for data protection, access control, and accountability, minimizing the attack surface and ensuring data integrity. Incorrect approach is analysis. Granting broad administrative privileges to a limited group of users, even if they are trusted, is a significant regulatory and ethical failure. This violates the principle of least privilege, increasing the risk of accidental or malicious data compromise. It also makes auditing less effective, as it becomes harder to pinpoint specific actions to individuals when privileges are overly generalized. Implementing only basic password authentication without any multi-factor authentication or robust password policies is another regulatory failure. This leaves the system vulnerable to brute force attacks and credential stuffing, failing to meet modern security standards and regulatory expectations for protecting sensitive data. Disabling auditing to improve performance is a critical regulatory and ethical lapse. Auditing is a fundamental requirement for demonstrating compliance, detecting security incidents, and conducting investigations. Disabling it creates a blind spot, making it impossible to verify access controls or identify unauthorized activities, which would be a direct violation of most data protection regulations. Professional reasoning. Professionals should approach DB2 security configuration by first understanding the specific regulatory requirements applicable to their environment. This involves identifying sensitive data, defining user roles based on business functions, and mapping these roles to specific database privileges. The next step is to implement strong authentication mechanisms that align with enterprise security policies and regulatory mandates. Subsequently, a granular RBAC model should be designed and implemented, adhering to the principle of least privilege. Finally, auditing should be configured to capture all relevant security events, with regular review and retention policies established to meet compliance needs. This systematic, risk-based approach ensures that security controls are effective, efficient, and compliant. Question 7. The performance metrics show a significant increase in query response times for critical reporting functions. Analysis of the database schema reveals that several tables involved in these reports are not adequately indexed for the types of joins being performed, and there is a lack of clear primary key enforcement on some historical data tables, potentially leading to data inconsistencies. Which approach best addresses these performance and integrity concerns within the relational database model? Option A. Introduce a materialized view that pre-aggregates the data required for the reports, thereby reducing the need for complex joins and improving read performance, even if it introduces some data redundancy. Option B. Increase the buffer pool size and tune other memory-related parameters to allow more data to be cached, assuming that the performance bottleneck is primarily due to I/O limitations rather than structural issues. Option C. Denormalize the reporting tables by merging columns from related tables into a single, wider table to minimize the number of joins required for report generation. Option D. Implement a comprehensive indexing strategy based on the observed query patterns, ensuring that primary keys are defined and enforced for all tables to guarantee referential integrity and optimize join operations. The correct answer is D. Implement a comprehensive indexing strategy based on the observed query patterns, ensuring that primary keys are defined and enforced for all tables to guarantee referential integrity and optimize join operations. Explanation. This scenario presents a common challenge for IBM certified database administrators, optimizing database performance while maintaining data integrity and adhering to relational database principles. The core difficulty lies in balancing the need for speed with the fundamental requirements of a well-structured relational model. Incorrectly prioritizing one aspect over another can lead to data corruption, performance degradation, or non-compliance with established database design best practices. The correct approach focuses on understanding the root cause of performance issues within the context of the relational model. This involves analyzing query execution plans, identifying inefficient joins, or recognizing suboptimal indexing strategies. By addressing these underlying relational database concepts, such as the appropriate use of primary and foreign keys for referential integrity, the strategic placement of indexes to accelerate data retrieval, and the selection of suitable data types to minimize storage and improve processing, the administrator ensures that performance gains are achieved without compromising the integrity or logical structure of the database. This aligns with the professional responsibility to maintain a robust and reliable database system, which is implicitly expected by any organization relying on the data. An incorrect approach that bypasses relational principles, such as denormalizing excessively without a clear understanding of the trade-offs, risks introducing data redundancy and anomalies. This can lead to update anomalies where changes to redundant data are not consistently applied, violating data integrity. Another incorrect approach might involve creating redundant or overly broad indexes without proper analysis. While indexes improve read performance, too many or poorly designed indexes can significantly slow down write operations, inserts, updates, deletes, and consume excessive storage, ultimately degrading overall performance and increasing maintenance overhead. Such actions demonstrate a lack of understanding of how indexes interact with the relational model and can lead to inefficient resource utilization, a failure in professional duty to optimize effectively. Professionals should approach such situations by first thoroughly diagnosing the performance bottleneck using database-specific tools. This diagnostic phase should always be followed by an evaluation of potential solutions against the principles of relational database design and data integrity. A structured decision-making process involves 1. Identifying the problem, 2. Brainstorming potential solutions, 3. Evaluating each solution based on its impact on performance, data integrity, maintainability, and adherence to relational principles, and 4. Implementing the most suitable solution with thorough testing and monitoring. Question 8. Strategic planning requires a database administrator to evaluate potential methods for optimizing DB2 database performance, considering the need for robust data management and adherence to industry best practices, which approach best balances immediate performance gains with long-term system stability and data integrity. Option A. Relying solely on automated performance tuning tools provided by DB2 without manual verification or understanding of the underlying data structures. Option B. Conducting a thorough performance baseline assessment, analyzing query patterns, and performing impact analysis of proposed optimizations on data integrity and security before implementation. Option C. Immediately applying all available DB2 performance tuning parameters to maximize throughput, assuming that increased speed is the sole objective. Option D. Implementing aggressive indexing strategies and query tuning based on initial performance metrics without a comprehensive impact analysis. The correct answer is D. Implementing aggressive indexing strategies and query tuning based on initial performance metrics without a comprehensive impact analysis. Explanation: this scenario presents a professional challenge because a database administrator must balance the immediate need for performance improvements with the long-term implications of data integrity and compliance. The IBM Certified Database Administrator DB2 certification implies adherence to best practices and regulatory frameworks relevant to data management within the scope of DB2. While the specific jurisdiction is not explicitly stated for this exam, the principles of data governance and security are universally critical. Therefore, the administrator must consider how any proposed solution aligns with established data protection principles and potential audit requirements. The correct approach represents best professional practice because it prioritizes a thorough understanding of the existing environment and the potential impact of changes before implementation. This aligns with the principle of due diligence, ensuring that any modifications are well documented, tested, and do not inadvertently compromise data security or violate any implicit or explicit regulatory requirements related to data handling. A proactive, analytical approach minimizes risk and ensures that performance enhancements are sustainable and compliant. An incorrect approach that bypasses proper analysis and testing poses significant regulatory and ethical failures. Implementing changes without understanding their full impact could lead to data corruption, unauthorized access, or performance degradation that violates service-level agreements. From a regulatory standpoint, this could result in noncompliance with data privacy laws, e.g., GDPR if applicable, or similar frameworks governing data handling, leading to potential fines and reputational damage. Ethically, it demonstrates a lack of professional responsibility to safeguard data and maintain system integrity. Professionals should employ a structured decision-making process that begins with clearly defining the problem and its desired outcome. This is followed by researching potential solutions, evaluating their pros and cons against established criteria, including performance, security, compliance, and cost, and then selecting the most appropriate option. A critical step is to conduct impact assessments and pilot testing before full deployment. Continuous monitoring and documentation are also essential to ensure ongoing effectiveness and compliance. Question 9. The risk matrix shows a high probability of application performance degradation and potential instance instability if DB2 instance parameters are not carefully configured. You are tasked with optimizing the performance of a critical DB2 instance. Which approach best mitigates these risks while achieving performance gains? Option A. Disabling all instance monitoring features to reduce system overhead and focus solely on application performance metrics. Option B. Implementing a series of incremental changes to key instance parameters, monitoring the impact of each change on system performance and resource utilization, and reverting if negative effects are observed. Option C. Increasing all memory-related instance parameters to their maximum, allowed values to ensure ample resources are available for all operations. Option D. Adjusting instance parameters based on common best practice recommendations found in online forums without specific analysis of the current workload. The correct answer is D. Adjusting instance parameters based on common best practice recommendations found in online forums without specific analysis of the current workload. Explanation: this scenario presents a common challenge for database administrators, balancing performance optimization with system stability and resource management during instance configuration. The risk matrix highlights potential negative impacts on application availability and data integrity if instance parameters are not set appropriately. Careful judgment is required to select parameters that enhance performance without introducing instability or exceeding allocated resources. The correct approach involves a systematic and data-driven method for tuning instance parameters. This best professional practice is rooted in understanding the specific workload of the DB2 instance and the underlying hardware. It prioritizes making incremental changes, monitoring their impact, and reverting if negative consequences arise. This aligns with general IT best practices for change management and risk mitigation, ensuring that any configuration adjustments are deliberate and their effects are understood. While no specific IBM DB2 regulations are cited, the principle of due diligence and responsible system administration is paramount. An incorrect approach would be to arbitrarily adjust parameters based on anecdotal evidence or generic recommendations, without understanding the specific context. This could lead to performance degradation, increased resource consumption, or even instance crashes, directly impacting application availability and potentially leading to data corruption. Such actions demonstrate a lack of professional rigor and a failure to adhere to sound system administration principles. Another incorrect approach would be to ignore monitoring data, assuming that initial settings are optimal. This oversight can lead to undetected performance bottlenecks or resource exhaustion, which can have cascading negative effects on the entire system and its users. The professional decision-making process for similar situations should involve 1. Thoroughly understanding the current system workload and performance metrics. 2. Researching and understanding the impact of specific instance parameters on performance and resource utilization. 3. Implementing changes incrementally and in a controlled manner, ideally during off-peak hours. 4. Rigorously monitoring the system after each change to assess its impact. 5. Having a rollback plan in place in case of adverse effects. 6. Documenting all changes and their outcomes. Question 10. Benchmark analysis indicates that several critical DML operations within a high-volume DB2 database are exhibiting significant performance degradation, impacting application response times. The database administrator must address these issues efficiently and effectively. Which of the following approaches best represents a professional and compliant strategy for optimizing these DML operations? Option A. Focus solely on upgrading the server's hardware resources, such as increasing RAM and CPU, without investigating the specific DML statements or database configuration. Option B. Disable transaction logging for the affected tables to reduce overhead, thereby speeding up all DML operations. Option C. Systematically analyze query execution plans for select statements, evaluate the effectiveness of existing indexes, and consider the use of appropriate indexing strategies or materialized query tables for insert, update, and delete operations. Review and refine where clauses, explore batch processing techniques, and ensure efficient data loading utilities are utilized. Option D. Immediately rewrite all select statements to include performance hints and modify update and delete statements to remove complex where clauses, assuming this will universally improve performance. The correct answer is C. Systematically analyze query execution plans for select statements, evaluate the effectiveness of existing indexes, and consider the use of appropriate indexing strategies or materialized query tables. For insert, update, and delete operations, review and refine where clauses, explore batch processing techniques, and ensure efficient data loading utilities are utilized. Explanation. Scenario analysis. This scenario presents a common challenge in database administration where performance bottlenecks are identified during routine benchmark analysis. The core difficulty lies in optimizing data manipulation operations, insert, update, delete, select, without compromising data integrity, security, or compliance with IBM-specific guidelines for DB2 administration, which are the sole regulatory framework for this exam. The pressure to resolve performance issues quickly must be balanced against the risk of introducing unintended side effects or violating established best practices. Correct approach analysis. The correct approach involves a systematic, data-driven method to identify the root cause of performance degradation. This includes analyzing query execution plans, scrutinizing index usage, and evaluating the efficiency of the DML statements themselves. For insert operations, this might involve batching or optimizing load utilities. For update and delete, it could mean refining where clauses or considering staged updates. For select statements, it typically involves query tuning, index creation or modification, and potentially materialized query tables. This approach aligns with IBM's recommended practices for DB2 performance tuning, emphasizing a thorough understanding of the database's internal workings and the specific workload. It upholds professional integrity by prioritizing data stability and performance gains through informed, deliberate actions, directly addressing the benchmark findings without introducing new risks. Incorrect approaches analysis. One incorrect approach is to immediately implement broad, unanalyzed changes to DML statements, such as adding hints or altering where clauses without understanding their impact on existing data or other queries. This is professionally unacceptable because it bypasses the diagnostic phase, risking performance degradation in other areas, data corruption, or unintended data modifications, which could lead to compliance issues if data integrity is compromised. Another incorrect approach is to focus solely on hardware upgrades without investigating software-level optimizations. While hardware can be a factor, neglecting to tune the database and queries is a failure to apply best practices and can be an inefficient use of resources, potentially masking underlying DML inefficiencies. This also fails to demonstrate professional due diligence in exploring all avenues for optimization. A third incorrect approach is to disable logging or other integrity checks to speed things up. This is a severe ethical and professional failure, as it directly compromises data durability and recoverability, violating fundamental database administration principles and IBM's implicit requirements for maintaining a robust and reliable database system. Professional reasoning. Professionals should approach performance issues by first establishing a baseline through benchmarking. Then, they must systematically diagnose the problem using available tools, e.g., DB2 explain monitoring tools. This diagnostic phase should inform the selection of optimization strategies, prioritizing those that address the identified bottlenecks with minimal risk to data integrity and system stability. Any proposed changes should be tested in a non-production environment before deployment. This methodical approach ensures that optimizations are effective, sustainable, and compliant with the established operational framework. Question 11. The evaluation methodology shows that during the initial phase of designing a new database schema for sensitive customer information within a DB2 environment, the administrator must consider potential security risks. Which of the following approaches best mitigates these risks by establishing a secure and manageable schema and object ownership structure? Option A. Create the schema and assign ownership to a specific, non-administrative user account that has only the minimum necessary privileges to manage and access the objects within that schema, with other users granted specific, limited permissions to individual objects as needed. Option B. Assign ownership of the schema and its objects to a dedicated, highly privileged administrative user account that has broad system access, ensuring all operations can be performed without permission delays. Option C. Grant public read and write access to all objects within the newly created schema to allow for maximum data accessibility and ease of integration with other systems. Option D. Rely on the default DB2 schema and object ownership settings, assuming they provide adequate security for most common use cases. The correct answer is B. Assign ownership of the schema and its objects to a dedicated, highly privileged administrative user account that has broad system access, ensuring all operations can be performed without permission delays. Explanation. This scenario presents a common challenge in database administration, balancing security and operational efficiency during schema design and object ownership assignment. The core difficulty lies in ensuring that access controls are robust enough to prevent unauthorized data modification or exposure, while also allowing authorized users and applications to perform their necessary functions without undue complexity or performance degradation. The IBM Certified Database Administrator DB2 exam emphasizes understanding how to implement these controls within the DB2 environment, adhering to best practices and potential regulatory requirements for data protection. The correct approach represents best professional practice because it proactively identifies potential security risks associated with schema creation and object ownership. By establishing a clear ownership model and implementing granular security permissions, the administrator minimizes the attack surface and ensures that only necessary privileges are granted. This aligns with the principle of least privilege, a fundamental security concept that is often implicitly or explicitly required by data protection regulations. For instance, if this were a US-based scenario, regulations like HIPAA or SOX would mandate such controls to protect sensitive data. The proactive risk assessment ensures compliance and reduces the likelihood of security breaches, which can have severe financial and reputational consequences. An incorrect approach that assigns ownership to a generic or highly privileged user, e.g., sysadmin, without a clear justification creates significant security vulnerabilities. This failure violates the principle of least privilege, as it grants excessive rights to a single entity, making it a prime target for compromise. If compromised, this single point of failure could lead to widespread data breaches or unauthorized system modifications, directly contravening data protection mandates. Another incorrect approach, granting broad public access to schema objects, is a severe ethical and regulatory failure. This completely disregards data confidentiality and integrity, exposing sensitive information to anyone, regardless of their authorization. Such a practice would be indefensible under any data protection framework and would likely result in severe penalties, including fines and legal action. A third incorrect approach, neglecting to define specific object ownership and relying solely on default DB2 settings, is also professionally unacceptable. Default settings are rarely optimized for security and can inadvertently grant unintended access. This lack of deliberate control demonstrates negligence in safeguarding data and can lead to compliance issues and security incidents. The professional decision-making process for similar situations involves a systematic risk assessment. First, identify all data assets and their sensitivity levels. Second, define user roles and their required access levels based on business functions. Third, design the schema with security in mind, establishing clear ownership and applying the principle of least privilege to all objects and users. Fourth, implement robust auditing and monitoring mechanisms to detect and respond to suspicious activities. Finally, regularly review and update security configurations to adapt to evolving threats and business requirements. Question 12. Compliance review shows that several critical financial reporting applications running on the IBM DB2 database are experiencing intermittent but significant performance degradation, with users reporting timeouts and slow response times. Analysis of DB2 monitoring data indicates a high rate of lock waits and occasional lock escalations occurring during peak processing hours. The database administrator is tasked with resolving this issue to ensure application stability and meet service level agreements. Which of the following approaches represents the most effective and professionally responsible method for addressing this lock contention problem? Option A. Immediately disable deadlock detection to prevent transactions from being terminated and allow them to eventually complete. Option B. Systematically lower the isolation level for all affected applications from repeatable read to cursor stability to reduce lock holding times. Option C. Increase the lock timeout value for all transactions to allow them more time to acquire necessary locks before timing out. Option D. Analyze the specific SQL statements and transactions contributing to lock contention, identify the root cause of the waits, and then strategically adjust isolation levels or optimize SQL queries where appropriate, while ensuring deadlock detection remains enabled. The correct answer is B. Systematically lower the isolation level for all affected applications from repeatable read to cursor stability to reduce lock holding times. Explanation. This scenario presents a common challenge for IBM certified database administrators managing DB2 environments, particularly concerning lock contention and its impact on application performance and data integrity. The professional challenge lies in balancing the need for data consistency, enforced by locking mechanisms, with the requirement for high application throughput and responsiveness. Mismanaging locking can lead to performance degradation, application timeouts, and even data corruption, all of which have significant business implications and can lead to regulatory scrutiny if they violate service-level agreements or data handling policies. The correct approach involves a systematic and data-driven analysis of lock contention. This includes monitoring lock wait times, identifying the specific applications and SQL statements causing contention, and understanding the isolation levels being used. Adjusting isolation levels is a critical tuning parameter. For instance, moving from a higher isolation level like repeatable read to a lower one like cursor stability can significantly reduce lock contention by shortening the duration locks are held, provided the application logic can tolerate the potential for non-repeatable reads or phantom rows. Analyzing lock escalation is also crucial. While it can reduce the overhead of managing many fine-grained locks, it can also increase the impact of a single lock by holding a table lock, potentially blocking more transactions. Effective deadlock detection and resolution mechanisms, often built into DB2, need to be understood and configured appropriately to minimize disruption. This approach represents best professional practice because it prioritizes understanding the root cause of the problem before implementing solutions, thereby minimizing unintended consequences and ensuring that performance tuning aligns with application requirements and data integrity needs. It adheres to the principle of least privilege and minimal impact when making system changes. An incorrect approach would be to indiscriminately lower isolation levels across the board, without understanding the application's transactional requirements. This could lead to data integrity issues, violating the fundamental principle of data accuracy and consistency, which is often a regulatory requirement for financial or sensitive data. For example, if an application relies on reading a consistent set of data within a transaction, lowering the isolation level could result in it reading data that has been modified by another transaction, leading to incorrect calculations or decisions. Another incorrect approach would be to disable deadlock detection, which is a critical safety mechanism. Failing to detect and resolve deadlocks would allow transactions to hang indefinitely, severely impacting application availability and potentially leading to data inconsistencies if transactions are eventually forced terminated without proper rollback. This failure to implement robust error handling and recovery mechanisms is a significant professional and ethical lapse. The professional decision-making process for such situations should involve 1. Understanding the business impact. What are the consequences of the current performance issues? What are the acceptable levels of performance and availability? 2. Data collection and analysis. Utilize DB2 monitoring tools to gather detailed information on lock weights, lock escalation, deadlocks, and SQL statement performance. 3. Root cause identification. Pinpoint the specific transactions, application, and SQL statements contributing to lock contention. 4. Impact assessment of potential solutions. Evaluate the trade-offs of adjusting isolation levels, modifying application logic, or tuning lock parameters. Consider the potential impact on data integrity and application behavior. 5. Phased implementation and testing. Apply changes incrementally in a test or development environment, followed by a controlled rollout in production with thorough monitoring. 6. Documentation and communication. Clearly document all changes, their rationale, and their observed impact. Communicate effectively with application owners and stakeholders. Question 13. System analysis indicates a planned upgrade of a critical DB2 database server to mitigate risks associated with data loss and ensure optimal performance post-upgrade. Which of the following sequences of DB2 utilities would provide the most comprehensive approach to data protection and system readiness? Option A. Perform a full database backup, followed by reorg on key tables and indexes, then execute runstats, and finally use DB2 look to capture the database schema. Option B. Export all data from the database to flat files, then restore these files to the new server and run runstats. Option C. Restore the database from a recent backup, then run reorg on all tables and indexes. Option D. Perform a full database backup, then immediately proceed with the upgrade without further utility execution. The correct answer is A. Perform a full database backup, followed by reorg on key tables and indexes, then execute runstats, and finally use DB2 look to capture the database schema. Explanation. Scenario analysis. This scenario presents a common but critical challenge in database administration, ensuring data integrity and availability during a planned system upgrade. The core difficulty lies in balancing the need for a swift and efficient upgrade with the absolute requirement to prevent data loss or corruption. A misstep in the backup and restore process can have severe financial and reputational consequences for the organization, potentially violating data protection regulations and service-level agreements. The administrator must meticulously plan and execute the procedures, understanding the nuances of each utility and their impact on the overall system state. Correct approach analysis. The correct approach involves a multifaceted strategy that prioritizes data safety and recoverability. This begins with a full, consistent backup of the DB2 database using the backup utility, ensuring all active transactions are committed and the backup image is usable for restoration. Following the backup, running the reorg utility on critical tables and indexes is crucial. This utility physically reorganizes data and index pages, reclaiming space and improving data access efficiency, which is beneficial before a major upgrade. Subsequently, executing runstats is paramount. This utility collects detailed statistics about the data distribution within tables and indexes. These statistics are vital for the DB2 optimizer to generate efficient execution plans for queries. Without up-to-date statistics, the optimizer might produce suboptimal plans, leading to performance degradation post-upgrade. Finally, using DB2 look to capture the database structure, DDL, is essential for recreating the database schema if a full restore from backup is not feasible or if specific schema adjustments are required. This comprehensive approach ensures that the database is not only backed up but also optimized, and its structure is documented, providing multiple recovery and validation pathways. This aligns with best practices for disaster recovery and business continuity, which are often implicitly or explicitly mandated by data governance policies and industry standards for data integrity. Incorrect approaches analysis. Performing only a backup without subsequent reorg and run stats is insufficient. While it ensures data can be restored, it fails to address potential performance issues that might be exacerbated by the upgrade or that already exist. This could lead to a degraded user experience post-upgrade, potentially violating service-level agreements and demonstrating a lack of proactive performance management. Exporting data using the export utility instead of a full backup is a critical failure. The export utility is designed for moving data between databases or for specific data extraction, not for full database recovery. It does not capture transaction logs or the complete database structure in a way that allows for a point-in-time restore. Relying on export for disaster recovery is a direct violation of data protection principles and would likely result in significant data loss if a restore were ever needed, leading to severe regulatory and financial penalties. Restoring from a backup without first running reorg and run stats, while technically possible, is a suboptimal approach. It means the database is restored in its potentially fragmented or inefficient state, and the optimizer is working with stale statistics. This directly impacts performance and can lead to extended downtime or poor application responsiveness after the upgrade, failing to meet operational efficiency standards and potentially impacting business continuity. Professional reasoning. Professionals must adopt a risk-based approach, prioritizing data integrity and availability. The decision-making process should involve understanding the purpose of each DB2 utility and its role in the overall data management lifecycle. Before any major operation like an upgrade, a thorough impact assessment is necessary, considering potential data loss, performance degradation, and recovery time objectives. This involves consulting documentation, understanding the specific DB2 version's capabilities, and adhering to organizational policies for data backup, recovery, and performance tuning. The goal is to implement a strategy that is robust, efficient, and compliant with all relevant data governance and operational standards. Question 14. Operational review demonstrates that a newly designed customer orders table in a DB2 database is experiencing slow query performance and occasional data inconsistencies. The table includes columns for order ID, customer ID, order date, product ID, quantity, and unit price. The current design uses varchar 255 for all text-based identifiers, a generic integer type for quantity and unit price, and no explicit primary or foreign key constraints. Indexes are only present on the order ID column. Which of the following design approaches would best address the observed issues and align with robust database design principles for this DB2 environment? Option A. Implement table partitioning on the order date column and use a generic bidgent for all numeric fields to accommodate a wide range of values. Option B. Increase the size of the varchar data types for all identifiers to varchar 500 to ensure ample space for future growth, and add a full-text index on the order date column for faster date-based searches. Option C. Redefine order ID, customer ID, and product ID to appropriate fixed-length character types or integers, unit price to a decimal type with appropriate precision, and quantity to a small one. Implement a primary key on order ID and foreign keys on customer ID and product ID. Create indexes on customer ID and product ID to support common lookup queries. Option D. Convert all numeric columns to varchar types to simplify data handling and remove all constraints and indexes except for the order ID primary key to improve insert performance. The correct answer is C. Redefine order ID, customer ID, and product ID to appropriate fixed-length character types or integers, unit price to a decimal type with appropriate precision, and quantity to a small one. Implement a primary key on order ID and foreign keys on customer ID and product ID. Create indexes on customer ID and product ID to support common lookup queries. Explanation. This scenario presents a common challenge in database administration, balancing performance, data integrity, and resource utilization during table design. The core difficulty lies in selecting appropriate data types and defining constraints that accurately reflect business rules, while minimizing storage overhead and maximizing query efficiency. The IBM Certified Database Administrator DB2 exam emphasizes a practical understanding of these design principles within the context of DB2 capabilities. The correct approach prioritizes data integrity and efficient storage through precise data type selection and appropriate constraint definition. Choosing a data type that closely matches the expected range and precision of the data, e.g., small int for small integer count, decimal for financial figures, prevents data truncation and unnecessary storage allocation. Implementing primary and foreign key constraints enforces referential integrity, a fundamental aspect of relational database design, ensuring data consistency and preventing orphan records. Indexing critical columns used in where clauses or join conditions significantly improves query performance, a key responsibility of a DBA. Table partitioning, when applicable, further enhances manageability and performance for very large tables by dividing them into smaller, more manageable segments. This holistic approach aligns with best practices for robust and performant database systems. Incorrect approaches often stem from a lack of thorough analysis or a focus on expediency over long-term maintainability and integrity. Using overly generic or large data types, e.g., varchar max for a fixed-length code, wastes storage and can negatively impact performance. Neglecting primary and foreign key constraints, while seemingly simpler initially, creates a high risk of data inconsistencies, violating the core principles of relational database design and potentially leading to inaccurate reporting and application errors. Failing to design appropriate indexes for frequently queried data will result in slow query execution, impacting user experience and application responsiveness. Implementing partitioning without a clear understanding of data access patterns or table size can lead to increased complexity and management overhead without tangible performance benefits. These oversights can lead to significant technical debt and operational issues. The professional decision-making process for similar situations involves a systematic risk assessment. First, thoroughly understand the business requirements and data characteristics. Second, evaluate DB2 data types and features to select the most appropriate options for storage efficiency and data integrity. Third, define constraints to enforce business rules and maintain referential integrity. Fourth, analyze query patterns to design effective indexes. Finally, consider advanced features like partitioning only when the benefits clearly outweigh the complexity and management overhead. This structured approach ensures that design decisions are data-driven, business-aligned, and technically sound. Question 15. The control framework reveals that a critical DB2 application is experiencing significant performance degradation. The database administrator is tasked with optimizing a frequently executed complex SQL query. Which of the following approaches represents the most effective and professionally responsible method for addressing this performance issue? Option A. Systematically analyze the query's access plan. Ensure statistics are current and accurate. Evaluate index usage, and leverage the SQL Tuning Advisor for recommendations before considering query rewriting. Option B. Rewrite the SQL query using a different syntax or structure based on common performance patterns observed in other applications, without detailed analysis of the current query's execution plan. Option C. Implement the first set of recommendations provided by the SQL Tuning Advisor without further investigation or validation of their impact on the overall system. Option D. Immediately create new indexes on all columns involved in the query's where and join clauses, as this is a common performance enhancement. The correct answer is A. Systematically analyze the query's access plan, ensure statistics are current and accurate, evaluate index usage, and leverage the SQL Tuning Advisor for recommendations before considering query rewriting. Explanation. Scenario analysis. This scenario presents a common challenge for IBM Certified Database Administrators, optimizing SQL query performance within a production DB2 environment. The challenge lies in balancing the immediate need for query speed with the long-term implications of chosen optimization strategies. Administrators must consider not only the technical effectiveness of a technique, but also its adherence to established best practices and potential impact on system stability and resource utilization. The pressure to deliver rapid performance improvements without introducing new issues requires a deep understanding of DB2 internal workings and a methodical approach to tuning. Correct approach analysis. The correct approach involves a systematic analysis of the query's access plan, focusing on identifying inefficiencies and leveraging DB2 built-in tools for performance tuning. This includes thorough statistics collection to ensure the optimizer has accurate information, careful examination of index usage to confirm appropriate indexes are being utilized, and strategic query rewriting when necessary. The SQL Tuning Advisor is a critical tool in this process, providing expert recommendations based on the collected statistics and the query's execution plan. This methodical, data-driven approach aligns with best professional practices by ensuring that optimization efforts are targeted, effective, and minimize the risk of unintended consequences. It adheres to the implicit regulatory expectation of maintaining system integrity and performance through responsible administration. Incorrect approaches analysis. Applying a one-size-fits-all index creation strategy without analyzing the access plan or statistics is a significant regulatory and ethical failure. This approach can lead to performance degradation due to unnecessary index maintenance overhead, increased storage requirements, and potentially incorrect index selection by the optimizer. It demonstrates a lack of due diligence and a failure to adhere to the principle of administering systems responsibly. Blindly rewriting SQL queries based on anecdotal evidence or without understanding the underlying access plan is also professionally unacceptable. This can introduce new performance bottlenecks, break existing functionality, or create complex, unmaintainable SQL. It violates the ethical obligation to ensure the stability and correctness of the database system. Relying solely on automated tools without human oversight or validation is another failure. While tools like the SQL Tuning Advisor are powerful, they are aids, not replacements for expert judgment. Over-reliance can lead to suboptimal solutions or the implementation of recommendations that are not suitable for the specific operational context, potentially impacting system performance and availability. Professional reasoning. Professionals should approach SQL optimization by first establishing a baseline of current performance. This is followed by a comprehensive analysis of the query's access plan using tools like Explain. Accurate and up-to-date statistics are paramount for the optimizer. Based on this analysis, specific tuning techniques such as index optimization, query rewriting, or leveraging the SQL Tuning Advisor should be considered. Each change should be tested in a non-production environment and its impact carefully monitored after implementation in production. This iterative, analytical, and cautious approach ensures that performance improvements are achieved responsibly and sustainably. Question 16. Stakeholder feedback indicates that while application servers require reliable network access to the DB2 database for critical business operations, the security team has mandated a significant reduction in the database's network exposure to mitigate potential cyber threats. The current configuration uses the default TCP/IP port and has broad firewall exceptions. Which of the following network configuration strategies best balances these competing requirements while adhering to robust security principles? Option A. Leave DB2 listening on the default TCP/IP port and implement broad firewall rules that allow inbound connections from any IP address to this port, assuming the application servers will handle their own security. Option B. Disable TCP/IP communication for DB2 entirely and instruct all applications to connect locally to the database server. Option C. Configure DB2 to listen on a specific, non-default TCP/IP port and implement firewall rules that strictly permit inbound connections to this designated port only from the IP addresses of the authorized application servers. Option D. Configure DB2 to listen on a custom TCP/IP port, but implement overly restrictive firewall rules that block all inbound traffic, including from authorized application servers, to ensure maximum security. The correct answer is C. Configure DB2 to listen on a specific non-default TCP/IP port and implement firewall rules that strictly permit inbound connections to this designated port only from the IP addresses of the authorized application servers. Explanation. Scenario analysis. This scenario presents a common challenge in database administration where security and accessibility requirements for a DB2 database conflict. Stakeholders need reliable access for application connectivity, while the security team mandates stringent network controls to protect sensitive data. Balancing these competing needs without compromising either requires a deep understanding of TCP/IP networking, DB2 network configuration, and relevant security best practices, all within the context of the IBM Certified Database Administrator DB2 exam's assumed regulatory framework, which, for this exam, implies adherence to general IT security principles and best practices common in enterprise environments, without specific jurisdictional mandates unless explicitly stated. The challenge lies in implementing a solution that is both functional and secure, avoiding common misconfigurations that could lead to vulnerabilities or performance issues. Correct approach analysis. The correct approach involves configuring DB2 to listen on a specific, non-default TCP/IP port, and ensuring that firewall rules are precisely defined to allow inbound connections only to this designated port from authorized application servers. This is best professional practice because it minimizes the attack surface by not exposing DB2 on a well-known or default port that attackers might scan for. Explicitly defining firewall rules ensures that only legitimate traffic can reach the database, adhering to the principle of least privilege. This configuration also allows for easier network troubleshooting and monitoring, as traffic to the database is isolated to a known port. This aligns with general IT security best practices and the implicit requirements for responsible data management expected of a certified professional. Incorrect approach is analysis. One incorrect approach is to leave DB2 listening on the default TCP/IP port e.g. 50,000 and rely solely on broad firewall rules that permit inbound connections from any IP address to that port. This is a significant security failure because it exposes the database to a wide range of potential threats, making it an easy target for port scanning and brute force attacks. It violates the principle of least privilege and significantly increases the risk of unauthorized access. Another incorrect approach is to configure DB2 to listen on a custom, but still widely accessible, port, and then implement overly restrictive firewall rules that block all inbound traffic, even from legitimate application servers. While this prioritizes security, it renders the database inaccessible to its intended users and applications, failing to meet the core business requirement of accessibility. This demonstrates a lack of understanding of how to balance security with operational needs. A third incorrect approach is to disable TCP/IP communication for DB2 entirely and rely solely on local connections. This is incorrect because many enterprise applications and distributed systems require network access to the database. Disabling TCP/IP would severely limit the database's utility and prevent its integration into the broader IT infrastructure, failing to meet stakeholder requirements for application connectivity. Professional reasoning. When faced with conflicting stakeholder requirements regarding network access and security for a DB2 database, a professional should first understand the specific needs of each stakeholder group. The next step is to research and apply established best practices for network security and database configuration. This involves understanding the implications of port assignments, firewall configurations, and DB2-owned network settings. The decision-making process should prioritize a layered security approach, implementing controls at both the database and network levels. Professionals should always aim for the most secure configuration that still meets functional requirements, employing the principle of least privilege and minimizing the attack surface. Regular review and auditing of network and security configurations are also crucial components of professional responsibility. Question 17. The control framework reveals that a proposed modification to the DB2 installation parameters, specifically altering the buffer pool sizes and log buffer settings, is being considered to improve application performance. Which approach best ensures that this change is implemented responsibly and without unintended negative consequences? Option A. Rely solely on the application team's recommendation and their testing results to justify the configuration changes. Option B. Conduct a detailed impact assessment that evaluates potential effects on system stability, security, and resource utilization, and document findings before proceeding. Option C. Proceed with the configuration changes immediately during off-peak hours, as the application team has indicated a strong need for performance improvement. Option D. Implement the changes incrementally, monitoring performance after each minor adjustment without a formal pre-change assessment. The correct answer is C. Proceed with the configuration changes immediately during off-peak hours, as the application team has indicated a strong need for performance improvement. Explanation: this scenario is professionally challenging because it requires a database administrator to balance the immediate need for system availability with the long-term implications of configuration choices, all within the context of established operational procedures and potential regulatory compliance. The impact assessment is critical for understanding how proposed changes to DB2 installation and configuration will affect performance, security, and overall system stability before implementation. The correct approach represents best professional practice because it prioritizes a thorough impact assessment. This aligns with the principles of responsible IT management and, in many regulated environments, is a de facto requirement for change management. By evaluating potential consequences on system performance, security posture, and adherence to data governance policies, the DBA ensures that changes are implemented in a controlled and predictable manner, minimizing risk and maintaining system integrity. This proactive stance is essential for preventing outages, data breaches, and non-compliance issues. An incorrect approach that bypasses or inadequately performs an impact assessment is professionally unacceptable. It represents a failure to adhere to due diligence and risk management principles. Specifically, it could lead to unforeseen performance degradation, impacting business operations and potentially violating service level agreements, SLAs. Introduction of security vulnerabilities, exposing sensitive data to unauthorized access or modification, which could have severe legal and financial repercussions. Configuration drift from established standards, making future maintenance and troubleshooting more difficult and increasing the likelihood of errors. Noncompliance with internal policies or external regulations governing data handling and system operations, leading to audits, fines, or reputational damage. The professional decision-making process for similar situations should involve a structured approach to change management. This includes 1. Understanding the proposed change and its objectives. 2. Conducting a comprehensive impact assessment covering technical, operational, security, and compliance aspects. 3. Documenting the assessment findings and potential risks. 4. Developing a rollback plan in case of unforeseen issues. 5. Obtaining necessary approvals based on the assessment. 6. Implementing the change during a scheduled maintenance window. 7. Verifying the successful implementation and monitoring system behavior post-change. Question 18. Benchmark analysis indicates that a financial services firm is experiencing performance degradation and increased application errors related to its core customer transaction database, managed by DB2. The development team has proposed several immediate schema modifications to address new reporting requirements and optimize query performance. The database administration team needs to decide on the most appropriate strategy for implementing these changes while ensuring data integrity and minimizing downtime. The proposed changes include creating new tables for aggregated data, altering existing tables to add new columns and modify data types, dropping obsolete tables, and creating new indexes on frequently queried columns. Additionally, the team is considering reorganizing the schema structure by creating a new schema and migrating relevant tables into it. Option A. Implement all proposed schema changes directly in the production environment during peak business hours to expedite the resolution of performance issues and reporting gaps. Option B. Conduct a thorough impact analysis of each proposed DDL statement, test the changes in a staging environment that mirrors production, and then schedule the implementation of create table, alter table, drop table, and create index statements during a planned maintenance window, ensuring proper backups are taken. Option C. Proceed with dropping obsolete tables immediately without verifying dependencies to free up space, and then alter existing tables by directly modifying column data types without considering the impact on existing data. Option D. Create new tables and indexes without defining primary or foreign key constraints, and then proceed to drop existing indexes that are suspected of causing write contention without assessing their read performance impact. Correct answer is A. Implement all proposed schema changes directly in the production environment during peak business hours to expedite the resolution of performance issues and reporting gaps. Explanation. Scenario analysis. This scenario presents a common challenge in database administration, managing schema evolution and data integrity under strict regulatory compliance. The core difficulty lies in balancing the need for agile development and schema updates with the imperative to maintain data accuracy, security, and auditability, as mandated by IBM's internal governance and any applicable external regulations. Though for this exam, we focus solely on the DB2 framework and its implied best practices for data management. The pressure to deliver new features quickly can lead to shortcuts that compromise long-term data health and compliance. Correct approach analysis. The correct approach involves a systematic and controlled process for schema modification. Using create table with appropriate constraints, primary keys, foreign keys, not null, check constraints, establishes the foundational integrity of the data. Alter table is then used judiciously for modifications, always considering the impact on existing data and applications. Drop table is reserved for situations where the table is no longer needed and all dependencies are resolved. Similarly, index management, create index, alter index. Drop index is crucial for performance and data access, but must be done with an understanding of query patterns and potential locking issues. View management, create view, alter view, drop view, allows for logical data abstraction and security, and changes must ensure that the underlying table modifications do not break view definitions or grant unintended access. Create schema provides logical organization, and drop schema is a significant operation requiring careful dependency checks. This methodical approach ensures that schema changes are well documented, tested, and implemented with minimal disruption and maximum data integrity, aligning with best practices for robust database management. Incorrect approaches analysis. An incorrect approach would involve making ad hoc schema changes without proper planning or impact analysis. For instance, directly dropping a table without verifying application dependencies or backing up data would lead to data loss and application failures, a severe breach of data management principles. Altering a table in a way that violates existing constraints, e.g., changing a column to allow null when it was previously not null, without a strategy for existing null values, compromises data integrity. Creating indexes without understanding their impact on write operations, or dropping critical indexes that support essential queries would degrade performance and potentially lead to application timeouts. Modifying views without ensuring they still accurately reflect the intended data or security policies could expose sensitive information or break reporting mechanisms. Dropping a schema without ensuring all its objects are no longer in use or referenced would result in orphaned data and metadata inconsistencies. These actions represent a failure to adhere to fundamental database administration principles, leading to instability, data corruption, and potential compliance issues. Professional reasoning. Professionals should adopt a structured change management process. This involves 1. Understanding the business requirement driving the change. 2. Performing a thorough impact analysis, considering all dependent objects, applications, and data. 3. Developing a detailed plan for the change, including rollback procedures. 4. Testing the change in a non-production environment. 5. Obtaining necessary approvals. 6. Executing the change during a maintenance window if possible. 7. Verifying the change post-implementation. This systematic approach minimizes risk, ensures data integrity, and maintains system stability, which are paramount in professional database administration. Question 19. Process analysis reveals that a critical financial reporting application running on IBM DB2 experiences intermittent data discrepancies. The application performs multiple read operations within a single transaction to aggregate financial figures. The current transaction isolation level is read uncommitted. Administrators are considering changing this to serializable to eliminate all potential data anomalies, or to read committed as a potential performance improvement. Which of the following approaches best addresses the need for data integrity while considering performance implications in this scenario? Option A. Maintain read uncommitted isolation level, as it offers the highest concurrency and performance, and any data discrepancies are considered acceptable application-level issues to be handled by retry logic. Option B. Implement repeatable read isolation level, as it prevents non-repeatable reads and phantom reads, ensuring stable query results within a transaction. Option C. Implement read committed isolation level to prevent dirty reads and non-repeatable reads, offering a better balance between data consistency and performance for read-heavy transactions. Option D. Implement serializable isolation level for all transactions to guarantee absolute data consistency, regardless of the performance impact. The correct answer is C. Implement read-committed isolation level to prevent dirty reads and non-repeatable reads, offering a better balance between data consistency and performance for read-heavy transactions. Explanation. This scenario presents a common challenge in database administration, balancing data consistency with application performance under concurrent access. The core difficulty lies in selecting the appropriate transaction isolation level. Incorrect choices can lead to data corruption, inaccurate reporting, or application failures, all of which have significant implications for business operations and regulatory compliance. The IBM Certified Database Administrator DB2 exam emphasizes understanding how DB2 transaction management features interact with application requirements and the underlying data integrity principles. The correct approach involves selecting an isolation level that provides the necessary data consistency for the application's operations, while minimizing the performance overhead associated with stricter locking. For many typical business applications, read committed offers a good balance, preventing dirty reads and non-repeatable reads without the performance penalties of repeatable read or serializable, which can significantly increase locking contention and reduce concurrency. This aligns with the principle of least privilege in database access, applying only the necessary level of isolation to ensure data integrity without compromising performance unnecessarily. An incorrect approach would be to choose serializable for all transactions simply to guarantee the highest level of consistency. While this prevents all concurrency anomalies, it can severely degrade performance by introducing extensive locking, leading to increased transaction wait times and potential deadlocks. This can indirectly impact regulatory compliance if systems become unresponsive or data cannot be accessed within required timeframes. Another incorrect approach is selecting read uncommitted. This level is highly susceptible to dirty reads, non-repeatable reads, and phantom reads, which can lead to applications processing and acting upon data that is not yet committed or has been rolled back. This directly violates fundamental data integrity principles and can result in significant financial or operational errors, potentially leading to regulatory scrutiny if financial or sensitive data is compromised. Choosing repeatable read might be acceptable in some scenarios, but can still introduce phantom reads, which might be problematic for applications requiring absolute stability of query results within a single transaction. Professional decision-making in such situations requires a thorough understanding of the application's data access patterns, the criticality of data consistency for each operation, and the performance implications of different isolation levels. It involves a trade-off analysis, prioritizing data integrity where essential and optimizing for concurrency where possible. This requires collaboration with application developers to understand their specific needs and potential failure modes. Question 20. Assessment of a DB2 database administrator's strategy for optimizing query performance in a high-traffic e-commerce application, considering the trade-offs between data integrity and response times. The application experiences significant read operations for product catalogs and order history. The administrator has identified that complex joins in the current normalized schema are impacting the speed of retrieving frequently accessed product details and customer order summaries. The administrator is evaluating different approaches to improve these read operations. Option A. Implement strategic denormalization by adding redundant columns to frequently queried tables, such as duplicating product descriptions or order line item details directly into the order header table, after rigorous performance testing and validation of data consistency mechanisms. Option B. Strictly adhere to BCNF for all tables, ensuring maximum data integrity and minimal redundancy, and rely solely on indexing strategies to improve query performance. Option C. Introduce redundant data without a clear performance analysis or a plan to manage data consistency, based on a developer's suggestion that it might improve performance. Option D. Denormalize all tables by merging them into a single, large table to eliminate all joins, regardless of the impact on data integrity or update complexity. The correct answer is A. Implement strategic denormalization by adding redundant columns to frequently queried tables, such as duplicating product descriptions or order line item details directly into the order header table, after rigorous performance testing and validation of data consistency mechanisms. Explanation. Scenario analysis. This scenario presents a common challenge in database administration, balancing the theoretical purity of normalization with the practical performance requirements of a production system. The administrator must decide whether to adhere strictly to normalization principles or to introduce controlled redundancy, denormalization, to improve query performance. This decision is professionally challenging because it involves trade-offs between data integrity, storage efficiency, and application responsiveness, all of which impact the overall usability and maintainability of the DB2 database. The administrator needs to consider the specific workload, query patterns, and the acceptable level of data redundancy. Correct approach analysis. The correct approach involves a strategic application of denormalization techniques after thorough analysis. This means understanding the normalization rules, 1NF, 2NF, 3NF, BCNF, and recognizing when strict adherence might lead to performance bottlenecks for critical queries. Denormalization, when applied judiciously, can reduce the number of joins required for frequent queries, thereby improving read performance. This is best professional practice because it demonstrates a pragmatic understanding of database design principles and their real-world implications. The decision to denormalize should be based on performance metrics, profiling, and a clear understanding of the trade-offs, ensuring that data integrity is maintained through other means, such as triggers or application logic, and that the increased redundancy is manageable. This approach aligns with the goal of creating efficient and effective database solutions for the business. Incorrect approach is analysis. One incorrect approach is to strictly adhere to BCNF without considering performance implications. While this ensures the highest level of data integrity and minimal redundancy, it can lead to complex queries with numerous joins, significantly degrading performance for read-heavy operations. This is professionally unacceptable as it prioritizes theoretical perfection over practical usability and business needs, potentially causing application slowdowns and user dissatisfaction. Another incorrect approach is to denormalize indiscriminately without understanding the normalization rules or the impact of redundancy. This can lead to data anomalies, update complexities, and increased storage requirements without providing significant performance benefits. It represents a failure to apply sound database design principles and can result in a poorly structured and difficult-to-maintain database, violating the implicit ethical responsibility to design robust and reliable systems. A third incorrect approach is to denormalize solely based on anecdotal evidence or without proper performance testing. This lacks the rigor required for professional database administration. It can lead to incorrect assumptions about performance gains and may introduce subtle data integrity issues that are hard to detect. This approach demonstrates a lack of systematic problem solving and can result in suboptimal or even detrimental design choices. Professional reasoning. Professionals should employ a decision-making framework that begins with understanding the business requirements and performance expectations. This involves 1. Establishing clear performance goals and identifying critical queries. 2. Designing the database initially following normalization principles, up to 3NF or BCNF where appropriate to ensure data integrity and minimize redundancy. 3. Profiling the database and identifying performance bottlenecks in critical queries. 4. Evaluating specific denormalization techniques, e.g., adding redundant columns, recalculating values that directly address identified performance issues. 5. Implementing denormalization incrementally and testing thoroughly to measure performance improvements and assess any impact on data integrity or update complexity. 6. Documenting all design decisions, including the rationale for denormalization and the measures taken to maintain data integrity. This systematic approach ensures that design decisions are data-driven, aligned with business objectives, and uphold professional standards of database design and administration.